Good morning, myself Nancy from Basic First Year making the video on chapter 4 alkane and cycloalkane. We make the video on cycloalkane. Introduction. Alphabetic cyclo compound are called acyclic. Acyclic form their ring structure compound. These compounds are so named because they resemble alphabetic compound in most of their property but process cyclic structure. However, due to their cyclic nature, they differ from alphabetic compound in some respect. Acyclic compound are also called carbonic compound since their rings are made up of carbon atom. Like open chain hydrocarbon alkyl compound are also been saturated, unsaturated, saturated acyclic compound corresponding to alkane or paraffin are called cycloalkanes, cyclopropanes. Those corresponding to alkane are called cycloalkene, while those who are corresponding to alkyne are called cycloalkynes. In this unit, we shall discuss the nomenclature, journal method of preparation, chemical properties, and the effect of ring size on the relative stability of cycloalkane. Nomenclature. The general formula of cycloalkane is CnH2n or CH2 bracket n, where n is 3, 4, 5, 6, etc. Since the alkanes are represented by the same formula, therefore cycloalkanes are isomeric with the alkane. Further, since in this compound a number of methylene units are joined together to form a ring, they are also called polymethylene. The name of any saturated acyclohydrocarbon then obtained by attaching the prefix tri, tetra, penta, hexa, etc. to the word methylene according to the number of carbon atom in the ring are 3, 4, 5, 6 respectively. In the IUPAC system, the saturated acyclic hydrocarbon are called cycloalkanes. The name of an individual cycloalkane is obtained by prefixing the word cyclo to the name of corresponding alkane having the same number of carbon atom as the ring. For conversing acyclic compound are usually represented by a simple geometrical figure are also called polygenic formula. A triangular for cyclopropane, a square for cyclobutane, a pentane for cyclopentane, a hexane for cyclohexane, and so on. In such representative, it was understood that each corner represented a CH2 group unless some other substitutes in the indicated. For example, cyclopropane, cyclobutane, cyclopentane, cyclohexane. IUPAC name of the substitute cycloalkane. The following rules are generally followed. In the case of substitution cycloalkane, the numbering of the ring carbon atom is done in a such a way that the substitute get lower possible number. The name of the substitute alkane is then obtained by prefixing the name of the substitute to the name of the parent cycloalkane. In the case there is more than one substitute. Each substitute prefix by its locality is arranged in alphabetic order before the name of the parent alkane. Ethylocyclopentane 1,2 dimethylcyclopentane 1-ethyl 2-methyl cyclohexane. Second, A. If the ring contains more or equal number of carbon atoms, then the alkyl group attached to it is named as a derivative of cycloalkane and the alkyl group is treated as a substituted group. Otherwise, it is named as a derivative of alkane and the cycloalkyl group is considered as a substitute group. For example, 2-methyl cyclohexane, pentocyclopentane, 3-cyclobutane. Noted that the parents are used whatever necessary to avoid confusion. Here in this first example, two butyl group has been enclosed in the parenthesis to emphasize that the locality to refer to the substitute on the alkene and the on the ring. B. If the however the side then the containing a multiple bond or a functional group acyclic is treated as substitute respectively the size of the ring. For example, 2 cyclopropyl 1 in 4 cyclohexabut 3 in 2 on. C. If, however, more than one acyclic ring is attached to a single chain, the compound is named as derivative of alkane and respectively of the number of carbon atoms in the ring or the chain. For example, dicyclopropyl methane 1,3-dicyclohexapropane. If a multiple double or triple bond and some other substitute are present in the ring, the number is done in such a way that the carbon atom of the multiple bond get lower locality 1 and 2 and the substitute group get the lower locality at the first point of difference. For example, 1,5-dimethyl cyclopentane 1 in 3-nitrocyclohex 1 in. Fourth, if the ring contain a multiple bond and the side chain contain a functional group, then the ring is treated as the substitute and the compound is named as derivative of the side chain. For example, 2-cyclopent 3-ethyl prop 1 ol and 3,4-methyl cyclohexane 2 in 1-yl propanoic acid. Fifth, if the ring as well as the side chain contain functional group, the compound is named as derivative of the side chain and the acyclic ring according as the side chain and or the ring containing the principal formula grouping. For example, 3,4-nitrocyclo 1 in line prop 2 in oic acid. If, however, the acyclic ring and the side chain contain the same functional group, the compound is named as derivative of the side chain of the ring according as the side chain or the ring containing the high number of carbon atom. For example, 2 hydroxybut 1-yl cyclohexanol. If the compound containing an acyclic ring directly linked to the benzene ring, it is named as derivative of benzene, the compound having the lowest state of hydrogenation. For example, cyclohexyl benzene. If seventh, if the functional group along with the other substitute group are present in the ring, it indicates that by the appropriate prefix and suffix, and its position is indicated by the numbering of the carbon atom of the ring in such a way that the functional group get the lowest number. For example, 3-methyl cyclohexane 1 all 5,6-dimethyl cyclohexane 2 in 1 on. Eighth, if an alkyl compound contains the carbon containing functional group, the carbon atom of the functional group are not indicated in the parent name of the alkylic system. Therefore, the system of the following prefix and suffix for the functional group are commonly used. CHO for meal carbohydrate, COOH carbyl carbolic acid, COX hydroxylic hydronyl halide, etc. IPC name of the haloalkanes. Many hydrocarbon and their derivative contain two or more rings. The carbon atom common to both the ring are called bridgehead atoms, and each bond chain of the carbon atom containing both the bridgehead atom is a bridge. Bridge may be contain 0, 1, 2, etc. carbon atom. For example, the bicyclic compounds are also named attach the prefix biocycle to the name of the hydrocarbon having the same total number of carbon atom in the ring. The number of the carbon atom in each of these tree bridge containing the two bridge head carbon atom is indicated by the Arabic number 0, 1, 2, etc. These Arabic number are arranged in descending order, separated from one another by a full stop and then enclosed into a square bracket. The complete IPC name of the hydrocarbon is obtained by the placing these brackets containing the Arabic number between the prefix bicyclic and the name of the alkane, containing the same total number of carbon atom as in the two ring. For example, biocyclobutane, biocycloheptane, biocyclic heptane, biocyclic 4001 decane. If the substitute is present, atom of the bicyclic ring are numbered, the numbering being with the one of the bridge head atom proceed first among the longest bridge to the second head atom, continue among the next longest bridge to the first head and finally completed among the shortest part. For example, 8 cyclo 321 octane biocyclo 221 heptane. Synthesis of cycloalkane and their derivatives. Some of the important methods of synthesis of cycloalkane and their derivatives are discussed below. Cycloadding reaction, an addition reaction between the two unsaturated compound molecules, ion or neutral species lead to the formation of a cyclic product are called cycloaddition reaction. In these reactions, the alpha electron of the two compound form the 2 alpha bond. These reactions are usually designed by writing the alpha electron of the two component usually in the descending order separated by a plus sign in a square bracket. For example, 2 plus 2, 4 plus 2, 6 plus 4. Cycloaddition reaction. For example, a 2 plus 2 cycloaddition reaction involves addition of two alkane molecules to form a cyclobutane derivative. These reactions do not involve ionic or free radical intermediate and occur a single step concentrated. Vice versa, the cyclic translation state in which bond making and bond breaking occurrence stimultaneously. Such concentrated reaction which occur through the cyclic translate are called pre-cyclic reaction, and these reactions do not require any catalyst and are intermediate either by heating or light. The following cycloaddition reaction can be used to prepare the cycloalkane. First, 2 plus 2 cycloaddition reaction. This is cycloaddition reaction can be used to prepare the both butane and cyclopropane derivative as a winning flow. First, synthesis of cyclobutane derivative. One of the most important method of synthesis of the cyclobutane derivative involves the addition of two molecules of the same or different alkene. These reaction occur under the photochemical condition by concentrated mechanism vice a cyclic translation state. For example, ethylene 2 molecule by the in the presence of HEV translated state say cyclobutane के अंदर. In the case of substitute alkane and although the addition take place on the same place of the superficial of the alkane where the two molecule of the alkane may approach each other in two different way give a mixture of wet two product. For example, cis 2 butane converted into the terra-methyl cyclobutane. Similarly, the terra-2-alkane is converted into. It may be noted here that the substitute alkane containing electron withdrawing substitute is such as fluoride, cyanide, ether from cyclobutane derivative under the terminal condition. This reaction produces via a free radical mechanism involving the diradical intermediate. Synthesis of cyclopropane derivative. Another example of 2 plus 2 cycloaddition involve the addition of free carbonyl or carbonyl to the alkene to give the cyclopropane derivative. First, addition of free carbene. Photolysis of the diazine methane in the presence of propane first give the methylene, which then added to propane to give the methyl cyclopropane. Methylene itself is reactive and hence give many side reactions exceptly interacting the reaction, which greatly reduce the yield of cycloaddition reaction. Halocarbene, on the other hand, being less reactive than the methylene, do not undergo the inserting reaction and hence give good yield of cycloaddition products. For example, cyclohexane in the presence of CCl2 give rise to 7,7-dichlorobicyco 4,2,1 heptane. Mechanism. The mechanism is believed to be occur by the following step. Photosynthesis of diazomethane give the methylene, which is highly reactive chemical species. The methylene text produced may be either singlet or triplet depending upon the reaction condition employed, such the wavelength of the light used, reaction phase, the presence of insert gas such as argon, nitrogen, and the presence of photosynthesizer singlet methylene is usually formed in the liquid phase photolysis, while the triplet methylene is produced either by the gas phase photolysis easily in the presence of the inert gas like N2 or argon, or by the photosynthesization. Second step. The methylene produced above add the across the double bond according to the cell. The mode of addition, however, depend on the type of methylene produced in step first. Singlet methylene reaction by a one-step mechanism give the stereospecific cis addition product. The stereochemistry of the organic alkane retained in the product, and in the another word, if in the original alkene the synthesized are trans, they will be trans in the product, and if they are cis they will be cis in the product. For example, cis 2 butane in the presence of single methylene transit to be cis 2 1,2 dimethyl cyclopropane, as the trans 2 butane in the presence of single methylene give rise to trans 1,2 dimethyl cyclohexane. The triplet methylene on the other hand react by the two-step free radical mechanism and give non-stereospecific addition product. For example, the reaction of either cis or trans butane with the triplet methylene give the same mixture of cis and trans 1,2 dimethyl cyclopropane. Similarly, we can show the trans 2,1,2-methylene by giving the mixture of the cis and trans dicycloalkanes. Second, addition of carbonyl cismos Schmidt reaction. Addition of methylene to the alkane give the lowest yield of cyclopropane derivative, since it being be extremely reactive undergo the main side reaction exclusively inserting the reaction. Therefore, when it is derived to add CH2 for the preparative purpose, the free carbene is used instead of carbon. Instead, a carbon-like species called a carbenoid is used, which is greatly improve the yield of the cycloaddition products by reducing the insert reaction. On such reaction is called Simo-Smith reaction, which is dioidomethane in the presence of Zn copper as a source of cyclobene like species. The addition is stereospecific since and occur by the converting mechanism as given below. On the other hand, the trans between the second 4 plus 2 cycloaddition reaction, Diels Alder reaction. This reaction involves the addition of alkane or alkyne molecule to pi electron called the diphenyl to conjugated diene. 4 pi electron result in the formation of 6-member ring. For example, cyclohexane is obtained by heating a mixture of butane and ethylene at 475 Kelvin. The Diler-Alter reaction does not require any catalyst. The two components are either heated together or heated in some solvents such as benzene, toluene, and cyclobenzene, etc. If the diphenyl contains an electron withdrawing group such as C double bond O, CHO, CO2H, CO2R, anhydride, quine, NO2, etc. The reaction can be carried out at much lower temperature. For example, 1,3-butadiene plus acrolein at 370 Kelvin may form the cyclohex 3 in 1 cycloaldehyde. Further, the greater the number of electron withdrawing group, more the reactivity is the diphenyl. Thus, the Diels reaction methyl anhydride is useful diphenyl, while the tetracyanoethylene is the most reactive diphenyl discovered so far. On other useful dienes are isopropene 2-methyl-1,1,3-butadiene and the cyclopentadiene. Stereochemistry. Diels reaction is the stereospecific cis addition reaction. The stereochemistry of the diphenyl is retained in the product. For example, cis cyclohex 4 in 1,2-dicarbolic acid in the presence of malic acid form the 1,3-butadiene. In the presence of formic acid, the but-1,3-butadiene converted into trans-cis hex 4 in 1,2-dichloric acid. If the diene is cyclic, two cis addition products are possible. These are called endo and the exoad product. In the endoduct, the molecule of the diphenyl lies under the that and the diene component, but in the exoduct, the two components project away from each other. It may be noted here that the dialdehyde reaction it is thermochemical and less stable endo product which always predominated over the other more stable exoproduct. Dehalogenation of the alpha beta and dihaloalkane Fidus method. This method involved the action of active matter such as zinc sodium on the stable alpha gamma dihaloalkane. Alkane having the halogen atom on the terminal carbon atom. This reaction may be regarded as intermolecular Woods reaction. For example, 1,3-dibromopropane in the presence of Jaden heated give rise to cyclopropane plus Jaden Br2. In this reaction, give the good yield only for cyclopentane alpha and gamma dihalide in which the two halogen atoms are further apart than the 1,6 position do not form ring compound but undergo the Wurtz reaction. For example, the Br dibromo CH2N give in the presence of Woods reaction then give rise to BrCH2 2N and Br2CH2 3N Br etc. Dieckmann cyclization or condensation. Ether is alpha gamma dicarbolic acid undergo the molecular classification condensation called the Dickman cyclization or condensation in the presence of molecular sodium or the sodium methoxide to form the cyclo beta ketoester. These cyclobeta ketoester on the substitute hydrolyze and decarbonization yield cycloalkanes, which can be converted to the corresponding cycloalkane by chemical reduction. For example, cyclopentane can be synthesized from diethyl adaptate by the following sequence of reaction. Dikimine condensation, in which diethyl adapted in the presence of NaOC2H5 plus, and the second is H plus H2O give rise to 2 carb ethyloxycyclopentanone. Second, hydrolysis of the 2-carb-ethyl cyclopentanone to the 2-carboxy cyclopentanone. This is useful acidic hydrolysis of the ether to the corresponding carbolic acid and is achieved by heating the ether with dilute HCl or H2SO4. Third, decarbonization of 2-carbolic cyclopentanone to the cyclopentanone. Since the 2-carbo-cyclopentanone is a beta ketoic acid, it readily undergoes the decarbonization on heating to give the cyclopentanone. Reduction of the cyclopentanone to cyclopentane. The conversion of cyclopentanone to cyclopentane is conventionally achieved by chemical reduction. Similarly, the Dykman cyclization can be used to prepare the cyclohexane from diethyl pramylate. Fourth, the pyrolysis of calcium or bromine salt of the dicarbolic acid by the Wisselians method. The calcium bromine thorium salt of the dicarbolic acid wild cycloalkanes on eating, which can be readily reduced to the corresponding cycloalkane by the chemical reduction. For example, barium adaptate in the presence of BaCO3, in the presence of Ba2 plus 565 minus 2 centigrade temperature give rise to cyclopentanone, and in the presence of chemical reduction give rise to the cyclopentanone. In according with the Balick rule, this method give the good yield of 5-6 membered ring. Balance rule. The effect of heat on the dicarbolic acid can be summarized in the form of balancing rule, which states that the dichloric acid in which the 2 carbolic group are attached to the same carbon atom upon heating undergo the decarbonization to form the monocarbolic acid 1,4 and 1,5 dicarbolic acid on heating alone or upon dilation with acetone and anhydride form the cycloanhydride 1,6 and 1,7 dichloric acid on heating alone or upon dilation with effect anhydride give the cycloketone, which with the loss of one carbon atom as a carbon dioxide, while 1,8 and higher dicarbolic acid remain unaffected. Tux. The rule is quite useful to determine the ring size of the cyclo compound. For this purpose, a double bond is introduced into the ring by some known method. The ring is then oxidized with the help of KMnO4 to give the dicarbolic acid, the pyrolysis of which help us to determine the size of the ring. Fifth, therapy Xyler reaction. This is the best method for preparation of large macrocyclic ring is good yield. It consists of treating an alpha gamma dinitrile, in which the nitrile group are at the terminal carbon atom with a base such as lithium diethylamide, commonly abbreviated as LDA, and lithium ethyl phenylamide is benzene or toluene. The dinitrile undergo an intermolecular condensation called tropy reaction to form a cyclic beta aminonitrile, which upon hydrolysis give the correct corresponding cyclic ketone in good yield. The cycloketone can then be reduced by the elimination method to give the corresponding cycloalkane. For example, the alpha beta dinitride in the presence of lithium nitride C2H5 give rise to the beta aminonitrile. Then in the presence of HH2 plus, the beta aminonitrile convert into beta ketonic acid, and the ketonic acid on heating convert into the cycloalkane, and in the presence of Kalmison reduction this is converted into cycloalkane. Like the diclinin cyclization, this method is good yield only for the 5,6 ring. However, by using the Zener higher dilution technology, the macrocyclic ring man been prepared in good yield. In the technology, a very dilute solution of dinitrile in benzene is added to the solution of the basis catalyst reaction in large excess ether. The ensure the intermolecular reaction by concentrable reducing the intermolecular reaction. In this way, the yield of 95%, 86%, and 68% ring with the 14 or more carbon has been obtained. The while 926 ring are however less than the 15%. Mechanism. The mechanism of the reaction is similar to the Dykman conduction, as it is evident from the formation of aminonitrile structure below. 6. Dim-Janov rearrangement. This is useful method for explanation expiration or concentration of acyclic ring system through the carbocation intermediate. The carbocation needed for the purpose are obtained by determination of acyclic alkyne with the nitrous acid. The initially formed carbocation may either react with a nitrophile to form the substitute product, or may be eliminated a proton to form an alkane. Elimination reaction. Alternative, this the initial formed cation may be undergo the rearrangement to more stable carbocation either by the ring expiration or concentration before undergoing the substitution or the elimination reaction method above. The ring expiration De-Genov rearrangement involved a ring expression when the carbocation intermediate has been positive charge on the carbon atom which is directly attached to the acyclic ring. For example, deaminization of cyclobutyl methyl amine give the methylocyclobutane cyclobutyl carbonyl as a normal product, while the cyclopentane and cyclopentanol are formed by the ring expression as given below. Ring concentration. The De-Genov rearrangement involved a ring concentration when the carbocation intermediate has a positive charge on the acyclic carbon atom. For example, deaminization of the cyclobutamine give a mixture of cyclobutanol and the cyclopropanol carbonyl. This is noted that here the carbocation first, second, and third do not eliminate a proton to form the corresponding ring alkane, because the cyclobutane and methylene cyclopropane are quite unstable due to angle strain. For the active methylene compound, a large number of acyclic compound has been synthesized by the action of active methylene compounds such as malonic ether or acetoacetic ether on the stable dialkane. Acyclic Carbolic ether tucks formed are hydrolyzed and decarboxylated when the cycloalkane are produced, for example, through the malic ether. It may be noted here that the cyclobutyrcarbolic acid tux obtained can be decarbolized directly since it undergoes a ring cleavage. However, it can be converted to the cyclobutane indirectly as discussed above. This is commonly known as Perkin method of preparation of cycloalkane. It instead of 1,3-dibromopropane, 1,2-dibromoethane, 1,4-dibromobutane are used in the above synthesized cyclopropanone, cyclopentane are synthesized. Second, through acetic acid. General physical properties. Cycloalkane closely resemble their open chain analogous and alkane in their physical property, although their melting point, boiling point, and density are somewhat higher. This is possible due to the reason that zigzag alkane molecules are constantly oscillating and hence cannot be closely packed in the crystalline lattice. On the other hand, cycloalkane, because of their rigid ring structure, overcome this oscillation to a great extent and hence are complementally more closely packed. This closer packing results in stronger intermolecular force called van der Waal of attraction, and hence the cycloalkane are hence melting has have the higher melting point than the corresponding alkanes. In the liquid state also the cycloalkane molecule are little more stronger held and hence have higher boiling point than the corresponding alkane. Further, because of the closely packed alkane, cycloalkane have higher density than the corresponding alkane. The melting point, boiling point, and density of the some cycloalkane are given in table 4.2. Like alkane, cycloalkane are non-polar molecule, hence are soluble in non-polar solvents such as carbon tetrachloride, petroleum ether, but insoluble in polar solvents such as water, alcohol. General chemical properties. Generally, the formula of cycloalkane is CnH2n, suggests that they should be unsaturated and hence should be resemble alkanes. However, because of the cyclic nature, they closely resemble alkane in their chemical property. This similarity to the alkane is attributed to the fact that all the carbon atom in these compounds, like in alkane, are sp3 hybridization, forming only CC carbon carbon and carbon hydrogen alpha bond, but all the cycloalkane are not easily quite unreactive. As such, they are not attracted by the chemical reagent like strong acid, strong alkyl, common oxidation agent KMNO, and powerful agent lithium aluminum hydride. However, like the alkane, they undergo the free radical substitution reaction. On the other hand, cyclopropane and cyclobutane show a higher degree of reactivity, cyclopropane being the particularly more reactive than the cyclobutane. This is due to the reason that the cyclopropane and cyclobutane ring are not very stable and hence tendency to undergo the ring cleavage formation. Addition product tux, they are resembled alkene under the addition reaction. However, they must be less reactive than the alkenes. Some of the important chemical reaction of the cycloalkane are described below. First, free radical substitution reaction. Cycloalkane undergo the type of free radical substitution uh, reaction when treated with the halogen at 2525 and 575 Kelvin in dark or at room temperature in the presence of light. For example, cyclopropane in the presence of Cl2 HV convert into the chlorocyclopropane. Second, addition reaction. It discuss like the alkane cyclopropane undergo the addition reaction. Some of the important addition reaction are. However, unlike the alkane, cyclopropane does not add ozone and other does not undergo the hydroxylation with the aqueous KMNO4 solution. Cyclobutane, on the other hand, is less reactive than the cyclopropane and hence does not undergo the addition reaction under the ordinary condition. Hence, on hydrogenation at higher temperature, it gives the N-butane. From the above discussion, it is evident that the cyclopropane is most reactive of all the cycloalkanes and undergoes many addition reaction through the ring cleavage. Cyclobutane is less reactive than the cyclopropane and undergo only addition of hydrogen, while the rest of the cycloalkane are unreactive and do not form the addition product. Instead, like the alkane, they wild substitution product. Now the question arises how account for this special behavior of 3 and 4 membered ring compound. Behavior, strain theory, and the relative stability of cycloalkanes. To explain the relativity stability of cycloalkane and the exceptional behavior of 3 and 4 member ring. Adolf von der Bever in 1885 proposed a theory known after his name as Bever state theory. This the main postulate of the theory argued under. First, a carbon atom bond to 4 other atom is tetrahedral and the angle between any pair of adjacent bond is tetrahedral 109 degree to 8. All the carbon atom consist a cycloalkane molecule lie in a plane. As a result, the bond angle between n two adjacent carbon atom are no longer equal to the normal tetrahedral angle of 109 degree 28. They are either less or more than the angle. Any derivative or distortion from this normal tetrahedral angle import strain and hence instability to the resultant molecule. Thus, this strain is commonly referred to an angle strain. The greater the derivation from the normal tetrahedral angle, greater is the angle strain and hence greater is the instability of the resultant molecule. Fifth, greater the stability of the ring, more easily it is formed. Extent of angle strain introduced depend on the size of the ring. In order to explain the relative stability of different alkene, let us determine the magnitude of angle strain in each one of them and the following expression. Angle strain is equal to half 109 degree minus 20 degree minus the bond angle in a planar ring. The cycloalkane ring can be regarded as an equilateral triangle with the angle of 60 degree. This implies that the angle strain in the cyclopropane equal to half 109 degree minus 60 is equal to 24 degree as shown in the figure A. On the other hand, cyclobutane ring is a square without the bond angle of 90 degree. Therefore, the angle strain in the cyclobutane is equal to half the 109 degree angle minus 90 is equal to 9 degree as shown in figure 4.2b. The following the same producer, we can calculate the angle strain in the various cycloalkane as given in the table 4.3. The positive value of the angle strain indicates that the bond angle are compressed, while the negative value means the expression of the bond angle from the tetrahedral angle. In both the cases, the molecule will be strained, and in another word, it is the magnitude of the angle strain. Note it sign which determine the strain and hence the inability of the molecule. From the table 4.3, if the flow it follow that angle strain fall rapidly in going from cyclopropane to cyclopentane and then increase slowly. This means that cyclopropane will be greater magnitude of angle strain, should be less stable and hence more reactive of all the cyclopropane, while the cyclobutane with less angle strain should be more stable, hence less reactive than the cyclopropane. Further, the cyclopentane with the least amount of angle strain should be most stable of all the cycloalkane. All these predications are in arrangement with the experimental fact. On the basis of this theory, Bever brigade of the course wrongly that the cyclohexane with more angle strain should be less stable than the cyclopentane and the ring larger than C7 carbon should not be exist. If at all this they exist, they should be highly strained and hence highly unstable. There will be no way to test these predications, hence the ring contains 7 or more carbon atoms were known at that time. Evidence in support of Baer strain theory. Some important points in the Baer strain theory are given below. First, reactivity of double bond. A double bond may be regarded as two-member ring with a carbon-carbon bond of 0 degree. Therefore, the angle strain is equal to 54 degree for 4. Since this angle strain is highest of all the cycloalkane, hence the alkenes should be higher reactivity, while there are argument with the observed fact reactivity of cyclopropane and cyclobutane. A comparison of heat of the comparison of heat of the combustion of cycloalkanes reveals that cyclopropane and cyclobutane poses more energy per CO2 group than the corresponding straight chain alkane. Constantly, there should be less stable than the corresponding N alkene. A fact in argument with the Weber strain theory that is therefore the resonance is to behavior that their tendency to undergo radiation reaction through the ring fusion is relative to this instability. Limitation of Baer strain theory. Bayes chain theory. Some of the limitations of Bayes chain theory are follow. First, on the basis of Bayes theory, the carbon-carbon double bond should be difficult to form since it is higher reactive and hence highly unstable. In contrast, it is known fact that a carbon-carbon double bond is easily formed by dehydrogenation of alkyl halide and dehydrogenation of alcohol, etc. On the basis of behavior strain theory, cyclohexane and the ring have 7 or more carbon atoms should be less stable than the cyclopentane, but the heat of combustion data revealed that cyclopentane and cyclohexane and the ring contain 7 or more carbon atoms are equally stable. Heat of combustion and relative stability of cycloalkane. We know that the heat of combustion is the amount of heat evolved when 1 mole of a compound is completely burnt to form a carbon dioxide and water. These furnish valuable information about the relative stability of organic compound. Let us now examine whether the heat of combustion of a various cycloalkane support the Beirut theory or not. Table 4.4 lists the heat combustion of the number of cycloalkanes. From the table 4.4, it is clearly that the heat of combustion per CH2 group should for the cyclopropane and cyclobutane are 696.4 and 685.5 kilojoule per mole. Lately, those for the cyclopentane and cyclohexane are 663.4 and 657.9 kilojoule per mole, respectively, as compared to the 657.9 per CH2 group of an alkene. A CH2 group has been expected to contribute equal to all the heat of combustion of a compound because it wields the same product of combustion CO2 and H2O. The CH2 plus 3 by 2 O2 give rise to CO2 plus H2O plus heat in respectively of this compound in which the CO2 group is present, but the fact that the cyclopropane and the cyclobutane involve more heat as per the CH2 group more the cyclopentane and cyclohexane or an alkane means that the cyclopropane and cyclobutane contain more energy as per the CH2 group than the cyclopentane and cyclohexane or an alkane. In another word, the cyclopropane and cyclobutane should be less stable than the cyclopentane and cyclohexane or just straight chain alkane, and this is argumented with the Weber's chain theory. According to Weber's chain theory, the ring larger than the cyclopentane and cyclohexane should be increasingly less stable due to corresponding increase in the magnitude of the angle as the ring size in increasing talks. If the Bevis chain theory was correct, then it should be accepted that the heat of combustion per CH2 of the alkane from the cyclopentane onward should visibly increase as the ring size increases. But the table 4.4 should note this is not true since the heat of combustion per CH2 alkane from cyclobutane onwards nearly remain constant and the value is closely to that of an alkane. This suggests that the cycloalkane and cyclopentane onward should be as stable as an alkene. Actually, the ring contains 7 to 11 carbon atoms are almost as stable as cyclopentane since they should be almost the same value of heat of combustion per CH2 group, but the heat of the combustion per CH2 group of cyclopentane and the ring contain the 12 or more carbon atom are about the same as that an alkane. In another word, in contrast of Weber's chain theory, cyclohexane and the ring contain 12 or more carbon atoms are completely free of the angle chain and hence as stable as an alkene. This is supported by the fact that these large ring compound such as cyclodecane, cyclodecpentanone and cis-tone perfume isolated from the civet cat, mucone perfume isolated from the mucoder, etc. Hence, been either synthesized in the laboratory or isolated from the natural source. One of these larger ring compound has been synthesized. They show the little or more tendency at all to undergo the ring opening reaction characteristic of the cyclopropane and cyclobutane. Squares-Moore theory of stainless ring. As discussed above, the previous theory could explain the relativity stability of containing 5 or less carbon atoms, but failed to account the stability of ring containing 6 or more carbon atoms to account for the stability of the 6-membered and large ring. Squares and Moore expand the model of cycloalkane and proposed this theory of stateless ring. According to this theory, carbon atom of five-membered and smaller ring can be a single plane as postulated by Beaver, but in the six-membered and larger ring they lie in different plane. In another word, the ring containing five or less carbon atoms are either planar or very nearly planar, but those of six or more carbon should be essentially non-planar or purposed. As a result, this puncturing each carbon atom retain its normal tetrahedral angle and there will be negligible or non-strain in the molecule. In further word, six-membered or large ring are stainless and hence the name of the theory of stainless ring. Further, the Sacris and Moore were able to contrast the model of two perpendicular form of cyclohexane and called the boat and chair form. These forms of cyclohexane are readily inconvertible by rotation above the single bond and hence represent the configuration of cyclohexane. Similarly, the ring larger than the six carbon atom can have negligible angle strain by assuming purpled perturbed arrangement of atoms in their molecules. Now this question arises, if the large rings are stable, why they are difficult to synthesize? Behavior assumption that the compound difficult to synthesize is nearly unstable is not correct. Actually, the ring closer to occur, it is essential that two ends of the carbon chain poses a functional group must become sufficiently closer to together to react with each other and evidently large ring to synthesize. The large must be the chain from which it is made up and hence less is the likelihood of two ends of the same chain approaching each other. Under this condition, there would be greater probability for the two different chain coupling together intermolecular condensation rather than the two ends of the same chain undergo the ring closure as shown in figure 4.4. This touches the difficulty of encountered in the synthesis of large number of rings as competing between the intramolecular condensation with the former predomination. However, recently this difficulty has been overcome by carrying out the reaction in higher dilute solution. Under this condition, the collision between the two different chains are minimized constantly and the ring closing reaction, although slow, and it is the principal reaction. The case of cyclopropane and banana bond. Cyclopropane offered the interesting case of bending the CC covalent bond. It planar molecule and its internal bond angle must be 60 degree. Therefore, there is constant considerable derivation from the tetrahedral angle, but the carbon cannot be hybridized orbital or alternated at the angle less than 90 degree to each other. The cyclopropane, the ring of a pi bond, cannot be formed by overlap of pure atom. To explain this improbability, has been shown that the hybridization of the orbital occurs in such a way that the ring formation orbital have a slightly greater p character than those of forming the normal pi bond between the carbon atom in saturated molecule. This explains why the angle pi between the two orbitals of one carbon atom in cyclopropane is 104 degree, little less that of the tetrahedral angle of 109 degree. Thus, the major axis of symmetry of the orbital forming carbon-carbon bond in the cyclopropane do not point toward one of the another but outward from the molecule with the result that the carbon single bond MO are not symmetrical but about their internuclear axis, but the band give the appearance of banana. It is because of this reason that the carbon-carbon bond in the cyclopropane are often referred to as bent or banana bond. Further, the due to the higher peak factor of hybridization orbital, there is smaller but appropriately pi decoloration around the ring. However, decoloration occur within the planar of the ring, not above or below the ring framework of the aromatic system. This in planar pi decorative add some the stability to the ring. Thank you.